Hi everyone, we're doing this chemistry paper today. This is 9701, paper 52, May June 2022. Let's begin. You have 1 hour 15 minutes to complete this, and you typically have two questions. Question 1 deals with designing an experiment, and in experiment 2, you have to fill up a table, followed by plotting a graph, finding out the gradient, answering some extra questions, okay? So remember to subscribe to the channel if you like the content, it will help me a lot. Hopefully, we reach 3,000 subs by the end of this year. Alright, let's begin. Before we start, I wanna take a look at the threshold. So for paper 5.2, you guys know that 30 is the highest mark. So A was at 20, B was at 18. That's a very small difference. C was at 15, D was at 13, and E was at 10. Okay. So U was probably around 5 or something, and A star was at around maybe 23 to 25, approx. That's not mentioned, but approximately it should be around 23 to 25, yeah? Approximately. So let's begin. So I have this done beforehand, so this will make the process easier for us. The student plans an experiment to find a value for the molar volume of hydrogen gas. Typically, we know that at room temperature it's supposed to be 24 dm cube. So hydrogen gas is formed when magnesium reacts with dilute hydrochloric acid. You guys know that magnesium plus any metal, if it's more reactive than hydrogen in the series, metal plus acid is equal to salt plus hydrogen gas. The test for hydrogen gas is it pops a lighted splint. Okay. So the student is provided with the following materials. We have a piece of magnesium ribbon, 0.50 mole per dm cube HCl, a water trough, a side arm conical flask, a 250 cm cube measuring cylinder with 2 cm cube graduations for the collection of gas, a 50 cm cube measuring cylinder, a balance that measures to 2 dB, access to any necessary laboratory experiment. So equipment except gas syringes. Okay, so we can't measure the volume of gas with the gas syringe. So we need to collect the gas in another way, mainly using this measuring cylinder over here. They've mentioned this over here, right? So the student plans the following procedure. Prepare the piece of magnesium ribbon for use in the experiment. Measure 30 cm cube of HCl and pour it into the sidearm conical flask. This is what a sidearm conical flask looks like. Okay, so you are given, wait, this is what you're given in the question. Nothing else, yeah? So this is a sidearm conical flask with a stopper. So we measure 30 cm cube of HCl and pour it into the sidearm. Then we attach the conical flask to a collection system for hydrogen gas. So since we don't have access to a syringe, I'll do other papers where I collect gas with a syringe in the future. But here we're collecting. There you can collect gas in two ways basically without using a syringe. Basically by using, you can collect it over water or under water. So it depends on the type of gas. Okay, so for hydrogen we use upward delivery. Okay, and for carbon dioxide, chlorine, and sulfur dioxide, we use downward delivery. It depends on density actually. Okay, so since hydrogen is less dense, so it has a tendency to go above. It also depends on solubility. So attach the conical flask to a system for collection of hydrogen gas. This is the system. I'm giving you the details in a bit. But it needs to be airtight, by the way, okay? No gas can escape. Place the magnesium ribbon in the conical flask. So there's a flaw in our system, okay? So after we, attach the system for collection of gas. We put the magnesium ribbon in. Okay, it falls down here, the reaction begins, and then we attach the stopper. So by the time the reaction has started, or by the time I have closed the vessel, some gas has escaped already. Okay, so this is a problem with the experiment, something that we need to fix later on. Basically, we need a method in which we can keep the stopper on, but the reaction won't begin. Okay, but in this method, the problem is we put the magnesium ribbon in, reaction has started, and then we put the stopper back in. By that time, some gas already escapes. That's an issue with the experiment. We're going to fix this later. Stopper the flask, wait until the final volume of gas collected is constant. Wait for additional 2 minutes, then measure and record the final volume of gas collected. Great. So we are asked to complete figure 1.1 to show how the apparatus should be assembled for the collection of the measurement of gas. Label your diagram. Okay, so let's begin. So we label the stopper and we have the side arm conical flask. So we are going to collect it over water. We are given a trough, right? We have a water trough and we have a 250 cm3 measuring cylinder for collection of the gas. Okay, so this is the tubing. It delivers the gas inside the water. It passes through the water trough. There are holes in the water trough which allows for the tubing to pass through, and then these are the bubbles of hydrogen gas which are collected over here. Okay, so we need to wait until the volume measured is constant. By the way, how do we measure the 30 cm3 of HCl? Using this 50 cm3 measuring cylinder. Okay, hopefully it makes sense. I have some other diagrams given here. Okay, this is how we do it. This is the water trough. Okay, that's all. The water trough has tubing, okay, so that has holes for the tubing to enter, perforations. So this is a sufficient diagram. All right. Moving on. Use the surface of magnesium ribbon has an oxide layer. Basically, like, remember aluminium oxide has a layer which makes it unreactive. It doesn't dissolve in water. Similarly, magnesium might actually react with the oxygen in air to form an oxide layer. So state how the student should prepare the piece of magnesium ribbon before it is used in this experiment. So we typically use sandpaper and rub the magnesium strip, okay, magnesium ribbon with the sandpaper to remove the oxide layer. I'll tell you what sandpaper is exactly. Check this, wait. This is what sandpaper looks like. Okay, so if we use this, if you use this, so using this to rub the magnesium ribbon, we can get rid of the oxide layer. That's sandpaper. It's just rough. State what additional information about the magnesium is required before the experiment is performed. Okay, so obviously we need the mass of magnesium because without that, we can't actually perform the molar calculation. Using mass by moles, mass by moles, or moles equals to mass by AR, we can find out the moles of magnesium, and then using molar ratio, we can find out the volume of the gas, right? We can match things basically. So that information, it's not placed here, but that's why the balance was given. We need that balance to measure the mass of magnesium, okay? So let's begin. Show by calculation that a volume of 30 cm cube of 0.5 mole per dm cube HCl is enough to react with 0.16 gram of magnesium ribbon. So HCl should be in excess. Let's begin. You can do this in two methods. So method 1, green one. So I'm finding out the mass, the moles of magnesium, which is 0.16 divided by 24.3. How did I get 24.3? At the end of the sheet, you have the data booklet. Magnesium is 24.3, okay? Basically, the periodic table. So that's 6.58 into 10 power minus 3 moles. So according to that, how many moles of HCl do we need? Double, because the molar ratio is 1:2. Does that make sense? Whoa, let's take 1:2. So double the moles, which is 0.0132. So now we can find out the volume of HCl required. How? We know that moles equals to volume by moles equals to volume into concentration. So volume is equal to mole by concentration. So 0.0132 divided by concentration gives us a value of 26.3 cm cube. That's the minimum amount required. We have 30 cm cube. So we have more than required. Okay. What is the alternate method, by the way? The alternate method is basically you could go the other way around. You could find out the moles of HCl that we have at present. Sorry. So that's 30 by 1000 into 0.50, which is 0.015. So according to the molar ratio, the amount of moles required for magnesium is actually half of that, 0.015 by 2. Okay, 0.015 by 2 is 0.0075, 7.5 into 10 power minus 3. So if you multiply that with the air of magnesium, you get a value of 0.18 grams. So here I just showed you guys that to react with 30 cm cube of HCl, 0.5 mole per dq HCl, we need 0.18 grams of magnesium. But we have 0.16 grams of magnesium. So magnesium is actually the limiting reagent here. Okay. State why it is not necessary to use a burette to measure 30 cm cube of 0.5 mole per dq HCl. So since magnesium is the limiting reagent, that means HCl is in excess. So burette is an instrument which is required for precision. Like for titration, it measures up to 2 decimal places. It's a precise instrument. So we only need a precise instrument when the volume really matters, when it has to be pinpoint, but the acid is already in excess. So even if we use a measuring cylinder, if it is not that precise, even if we get something like 30.5 cm cube or 29.5 cm cube according to the uncertainty of the measuring cylinder, it wouldn't really make a difference, guys. That's why when something is in excess, you don't need a precise instrument. Clear? So this next question is very, very important. Why does the student wait 2 minutes before taking a reading of the volume? Okay, this is very important. So you guys need to understand that this is an exothermic reaction. It generates heat. When you generate heat, a gas tends to expand, right? So you need to allow 2 minutes for the gas to actually, the heated gas to come down to room temperature. And in the process of doing so, the volume might decrease because it was heated beforehand, right? So we do this to make sure that the gas is at room temperature, or the heated gas comes down to room temperature, because the experiment was actually measuring the molar volume of hydrogen gas at room temp, okay, room conditions. Understood? Hopefully I could clarify this part. Let's go to the next part. The student collects 146 cm cube of hydrogen gas. Calculate the percentage error in collecting the hydrogen gas. Show your working. Very important. So guys, we need to look at the graduation. Uncertainty is actually half the smallest division of your measuring instrument. Okay, half the smallest division of your measuring instrument. So we use this measuring cylinder to measure the gas. The smallest division is 2. Okay, so the uncertainty will be 2 by 2, half of 2, which is basically 1 cm cube. Half the smallest division of your measuring instrument. So that's half into 2 cm cube, which is 1 cm cube. So the uncertainty will be or the percentage error will be uncertainty divided by actual value into 100%. So that's 1 cm cube divided by 146 cm cube into 100%. That gives us a value of 0.68. You have to give your answer to a minimum of 2 significant figures. Okay. Calculate the molar value of hydrogen gas using the student's results from the experiment. Okay. So guys, we know that like basically how to do it here in cm cube, right? So 0.16 grams of magnesium actually gave us 146 cm cube of hydrogen gas. So what would 1 gram give us? It would give unitary method 146 by 0.16 cm cube of gas. But what about 1 mole of magnesium? What about 1 mole of magnesium? Magnesium has an AR of 24.3. So 1 mole of magnesium or 24.3 grams of magnesium will actually give us volume of 146 divided by 0.16 times 24.3. So this gives us an answer of 22,174. Okay, this is basically unitary method. See if you guys understand the math. From the experiment, I found out that 0.16 grams gives us 146. So 1 gram gives us this much. And the AR of magnesium, 24.3 grams, or the molar mass of magnesium, gives us a volume of this the molar volume of hydrogen gas. Why is it the same? Why did I use the AR of magnesium? This is because, check this is the molar ratio of magnesium and hydrogen. It's actually 1:1. That's why when I use that, it actually gives us the molar volume of hydrogen, because 1 mole of magnesium, or 24.3 grams of magnesium, gives us 1 mole of hydrogen gas. Hopefully I could clarify. Now clearly this value, it should have been, you guys know that it should have been 24 dm cube or 24,000 cm cube. But check it out. The student's experimental value for the molar volume of hydrogen is lower than the value quoted in the table of important values on page 11. They're talking about this page over here, exactly here. It's supposed to be 24 dm cube at room temperature, right? So what's the reason actually? The reason is, remember I told you there was a flaw in the procedure. The student places the magnesium ribbon and then places the stopper, but in the time gap between these two steps, some gas already escapes. That's why the value or the volume of gas collected is underestimated. It's underestimated. It should have been higher, and if this value was higher, this numerator, it would have been closer to 24k. Suggest one experimental weakness that might have led to this outcome, and how could we overcome this weakness. So there is loss of hydrogen gas before the flask is stoppered between steps 4 and 5 essentially. Remember I was telling you guys there's some loss of gas here because it occurs suddenly. So human reaction time is not fast enough to prevent that, you know. So how could we prevent this actually? So this is a very common question that you guys are going to face in the question paper. Like, how are you going to improve this? You have to ensure that the reagents are separate. You have to ensure that the reagents are separate within the sealed flask before mixing. Okay. So the conical flask, sidearm conical flask, must be sealed. Okay, it needs to be sealed beforehand. And you need to ensure that there is a mechanism to prevent the magnesium ribbon from mixing with the HCl. So how is this done usually, if you guys are wondering? Honestly, this is how it's done. Typically, this is what we do. So this is the conical flask, right? We typically keep the ribbon in a vessel over here, and there's a hole in the stopper, okay? And basically it is connected to a burette over here, which is connected to a retort stand on the side like this. As a result, when we open the tap, or basically you could move this over here, okay? You could move this to this section. So when you open the tap, basically the acid falls here, and we maintain an airtight condition, right? We maintain an airtight condition, uh, and we prevent the loss of gas because we can measure 30 cm cube of acid from here, and we keep on putting it down, right, till we get 30 cm cube, and after a certain point they come into contact essentially, right? They come into contact, or you can make it drop on top of the magnesium ribbon itself. It would have been fine, honestly. Okay, so that's how we do it usually. We keep it in a separate vessel, something like this, something like this. Although it's a bit different, it's a bit different. Okay, So that this you'll be asked to draw this in some experiments. You'll be asked to, show how they're kept separate before mixing occurs. Okay, so that's it for question 1, guys. Hopefully you understood everything. Let's move on to question number 2. Important. Hopefully I can wrap this up within 20 minutes. In a neutral solution, aqueous potassium iodide acts as a catalyst for the decomposition of hydrogen peroxide. Potassium iodide is a good reducing agent. Halides are reducing agents. The color of potassium iodide is colorless, but iodide complex with silver is a yellow precipitate. Okay, a student plans to carry out an investigation to find how temperature affects the initial rate of decomposition of aqueous hydrogen peroxide in the presence of Ki. The student knows that the initial rate of reaction can be measured by timing the production of oxygen. The student carries out a series of experiments. In experiment 1, the student notes the temperature of the H2O2 and Ki under room conditions. The solutions are mixed in apparatus designed to collect the oxygen produced. A stopwatch is started at the beginning of the reaction. The volume of oxygen is noted at regular time intervals. In experiments 2 to 8, the solutions are heated to different temperatures before mixing, and the measurement of oxygen produced. The data collected is used to determine a value for the activation energy of the decomposition of hydrogen peroxide in the presence of Ki. So what is the independent variable here? Since we are changing the temperatures at the start of every experiment, right? So that's why something that you change beforehand is the it is actually the independent variable. Now, what about the dependent variable though? Okay, what about the dependent variable? There can only be two variables that change. Okay, so here temperature is the independent variable, and we are going to talk about the dependent variable, and all the other things have to be standardized, or else your experiment won't be valid. What does standardized mean? Basically they have to be kept at constant values. Understood? So what else are we adding here? We are adding potassium iodide to the mixture. We can only vary temperature to measure the rate at the end, but we are also adding potassium iodide as a catalyst. So clearly guys, it would be really unfair if we add more potassium iodide than required, in one experiment, and you add less in the other one. So we need to ensure that this is standardized, so we're going to add a same volume of potassium iodide, or you could go for catalyst. You could say that the same volume of potassium iodide or catalyst needs to be added, or the same volume of hydrogen peroxide needs to be used in each experiment. The same concentration of catalyst should be used, potassium iodide, or the same concentration of H2O2 should be used. So any two from these four. Clear? Moving on to part C1. State how the student should prepare 250 cm cube of 0.1 mol per dm cube H2O2 from 0.5 mol per dm cube H2O2. Okay, so we are basically going to perform dilution. Calculate the minimum volume of 0.500 mol per dm cube hydrogen peroxide required for preparation of the 0.100 mol per dm cube H2O2 solution. Give the name and capacity of any key apparatus which should be used. Okay. So for dilution, this is a very important part. Okay. Dilution will always be given, undoubtedly, right, in your questions. So you write your answer as a series of numbered steps. So let's begin. So we use the formula C1 V1 equals to C2 V2. So bio students are usually better at this because they've dealt with dilution from AS. So honestly, they're better. But you guys should know as chemistry students as well. So let's begin. So this is the formula C1 V1 equals to C2 V2, where C2 is the final concentration that we want, V2 is the final volume that we want, C1 is the initial concentration of the reagent that we used, and V1 is the unknown volume that we're gonna find out. Okay, so for example here, what's the final volume and concentration that we want? We want 250 cm cube of this 0.1 mol per dm cube solution. That's why in C2V2 I wrote 0.1 into 250. Okay, and what's the initial concentration that we had? We had 0.500 mol per dm cube. Does that make sense? So 0.5 into V1, this volume is unknown. This is the volume of the initial solution that we're supposed to use, is equal to 0.1 times 250. We get a value of 50 cm cube. Okay, so that's what they wanted us to calculate. Calculate the minimum volume of this required. That should be 50 cm cube. Okay, but listen, we want to prepare a 250 cm cube solution. Okay, so if 50 cm cube is the stock solution, this thing is called the stock solution. If we use 50 cm cube of the stock solution, then how are we going to make it up to 250? Basically, the other part, we use a volumetric flask essentially. So if 50 cm cube is the stock solution and we want 250 cm cube total, 250 minus 50 is essentially 200 cm cube. So the other 200 cm cube should be distilled water. Okay, so this is a common part that you'll find in each experiment. Very important. Okay, great. So let's begin. We need to talk about the apparatus that we use and how we do it. So guys, the first mark is for saying that you're going to use 50 cm cube of the stock solution. And what instrument are we going to use to do that? Using a burette, because we want precision here. We want precision, okay? So using a burette, we're going to transfer 50.00. In the mark scheme, they just mentioned 50, but this should be ideal for you guys. Because a burette measures up to 2 decimal places. So using a burette, transfer 50.00 cm cube of 0.500 mole per dm cube H2O2, hydrogen peroxide, to a 250 cm cube volumetric flask. Okay, so we need a burette, volumetric flask. We just transferred 50 cm cube there. Next, what are we going to do? Then we're going to top up the volumetric flask to the mark. Basically, there's a mark in the volumetric flask over here. So we are going to add distilled water up to the mark, okay? Because we want basically 200 cm cube. So we just add distilled water up to the mark. So they word it in this way. Since this is the latest mark scheme, you should follow it this way. So top up the volumetric flask, you know, up to the 250 cm cube mark with distilled water. So that's all for full marks. Hopefully you guys understood. By the way, I don't think you need to show the working. You can just do it on the side with a pencil. Okay, that's fine. This is the latest mark scheme. You should always follow this. Okay. By the way, I'll try to do paper 5.1/5.3 as well, if I get time before your exam. All right. So let's go to the next part. Hydrogen peroxide is an irritant. So what can we do to prevent, what precaution can we take other than wearing goggles? Okay, so we can just wear chemically resistant gloves. Okay, that's the point. This is pretty easy to do. Now let's begin, guys. We don't have much left. We just have a table. We have to plot the points, gradient, and just a few questions. We're just going to take 15 minutes. Let's go ahead then. In my February-March 2022 video, there was a mistake in the calculation of the gradient. I mentioned that in the comment, okay, with the link to the correct working, but everything else was fine except the gradient. Anyway, moving on. The student performs experiment 1 to 8 using a range of temperatures. Complete the table and record the values of 1 by T to 3SF and the values of log initial rate to 3SF. Unlike physics, in chemistry paper 5, they will tell you how many significant figures you're required to use. Okay, so for example, I'll show you the first one. 1 by 293 Kelvin. Do that with your calculator. 1 divided by 293. That gives you a value of 3.41297 into 10 to the power minus 3, which is basically 0.00341297. Okay, Kelvin to the power minus 1. So these zeros are not significant. So this is the first significant figure. So it's basically 0.00341. Okay, 0.00341. And if you need to round it off, please do round it off. For example, in the second one, 1 by 298 is 0.003557, which is 0.00356. So look, I just rounded it off since this value was greater than 5. Okay, hopefully that makes sense for all of you. that's how you fill up this table on the left hand side. Now what about the initial rate? So how to find out the initial rate? Log initial rate, just apply log. If they just say log, they mean log base 10. Okay, so do it. Log base 10, 5.75 into 10 to the power minus 6. So log base 10, 5.75 into 10 to the power minus 6. That gives you a value of minus 5.24033, which is minus 5.24. Great. So just like that, fill up the table. It should be pretty straightforward. You're going to get negative values on that side. And here. Oh, I want to tell you something else. Like in paper 5.1, I think there was a part where you had to use a value over here in this next part. So unlike physics, in physics paper 5, you have to use the raw value all the time. Okay, or else the answer won't mark with the match with the mark scheme. But in chemistry paper 5, guys, you can't use the raw value. You actually have to use this rounded off value in the next part. In this table we didn't actually require to do so, but in paper 5.1 we did. I'll try to make that video before 7th. I think your exam is on the 7th, I'm guessing, so I'll try to do that tomorrow. Okay, anyway, so after filling this table up, please try it out, try all the values. Let's move on to the next part. Oh, by the way, I forgot to mention this in my physics paper 5 videos, but do not use blobs. You cannot use blobs. Okay, what does that mean? This is not allowed. You can either use dots, or I personally prefer crosses. That's what I did in my exam, and I'm gonna recommend that to you guys as well. Just use crosses to plot data. Okay, so let's begin. So this is what the plots look like essentially. So for example, we have minus 4.20, the last point, and 0.00305. So minus 4.2 and 0.00305. That's on the spot over here. That's the cross. Then we have 4.28, minus 4.28 and 0.00308. So that's minus 4.28, 8 boxes down below, and 0.00308. So essentially, 2 boxes means 0.00306, 0.00307, 0.00308. So essentially the 2 boxes is equal to 0.00001 basically. Okay, so that's how it's done. So after 2 boxes, it ends up being 0.00306, 307, 308. So according to that, it's over here. You can look at the other ones. For example, 4.43, 0.00313. So 4.43, 3 boxes down below, 0.00313 over here, 6 boxes later. Okay, then we have 0.00321 and minus 4.66, minus 4.66, 6 boxes down below, and 0.00321. So just 2 boxes after 0.0032. And please look at the other points. Clearly this, no, this is fine, but minus 4.84 and 0.00325, minus 4.84, this one, 4 boxes below 4.8, and 0.00325. Clearly it looks like an anomaly compared to the other points, right? And these are the other points. Please check them out. If you do have any problems, you can match it with my graph. Okay, you can pause here if you want and check. I've plotted them perfectly. Now what do we need to do? Plot a graph, then draw a line of base fit. So unlike physics, in physics you need to make sure it is suitably distributed above and below the other points, but in chemistry there might be anomalies. So clearly the 1 2 3 4, the 5th point from the left hand side is an anomaly, so I'm going to exclude that and draw the line of base fit. This is what it looks like, the green line. check if it matches. I made it pass through the first point and the last point as well. It passes through all the points more or less, but it doesn't pass through this point 0.00325 and minus 4.84. That point is clearly an anomaly. Okay, this is what the graph looks like. Okay, then I'm gonna zoom out, see if you can see here. All right, let's move on then. Circle the point on the graph you consider to be the most anomalous. I just did that. So I suggest one reason why this anomaly may have occurred during this experimental procedure. Okay, to figure out the anomaly, usually you can answer it in two ways. But in recent mark schemes, I've been seeing that they only accept one way. Okay, so basically the logic is you can either think of it in two ways, like it should have been much higher up or it should have been to the right. Okay, here they are talking about the x-axis. So this is honestly the hardest mark in the question paper, the reasoning. Okay, and honestly this might be the reason you might get 29 out of 30, and it's hit or miss, so just it's up to luck. Okay, like there's no guarantee you're gonna score this, and you don't even need to. You're still gonna get an A star even if you mess this up, but with time you're gonna get better. So it should have been to the right. So what value is this actually, the x-axis? It's actually 1 by T, which is 1 by temperature. So basically it should have been like 0.00327, 0.00327, but it's 0.00325. Okay, so here you go, 1 by T. So the value of this should have been higher. That means the value of temperature should have been lower. For example, this anomalous point, this one over here, this temperature 308, 1 by T is too low. That means temperature is too high. What if rather than being 308, what if it was, a bit lower, like 305? What if it was 305? Yeah. So 1 by 305 is 1 divided by 305 is 0.00327. Isn't it fixed? Or 328? It's fixed now, right? Like I told you that it should have been slightly towards the right hand side. So basically there was something to do with temperature. So this temperature, the one that we've recorded over here, the problem was, honestly this was not, like here's the reason. The recorded temperature is higher than the actual temperature for that set of readings. The recorded temperature is higher than the actual temperature for that set of readings. So this recorded temperature over here, one sec, I can't seem to erase this. Wait. It's fine. Yeah. So the temperature should have been lower to match it, but the recorded temperature was actually higher. Okay, we have recorded a higher temperature than the actual one. It should have been something like 305 or something, but we have recorded it as 308. So the recorded temperature is higher than the actual temperature for that set of readings. That's the logic. So this was a mistake by the student performing the experiment. Okay, moving on. The next part is determining the gradient of your line of base fit. So you should honestly draw a triangle. I haven't drawn it here. State the coordinates of both the points used in calculation. These must be selected from your line of base fit. Give the gradient to three significant figures. So I think I've used minus 4.33, 4.43, and minus 5.10. Minus 5 because they pass through the the line of base fit. So here's my triangle. Minus 4.43 and 5.10. Okay, so wait. This is your triangle. The triangle should be greater than 50% of the graph, by the way. This works, I guess. Right? Yeah. So using them, I end up with 0.00313 minus 4.43 and 0.00336 minus 5.10. They're just values from the table. I could use them because my graph, my line of base fit passes through them. Yeah. So I get a value of minus 2910 Kelvin. And clearly it should be a negative value since the line has a negative gradient. Clear? So what is the gradient actually? And how are we going to use it? We're going to use it in the next section. So your answer shouldn't exactly be this. It might be along the lines of this. But since I've used data from the table, our answer should match. Okay, next. The relationship between log initial rate and 1 by t is given by this expression. Check this. Log initial rate is equal to constant minus activation energy divided by 2.303 RT, where R is the molar gas constant, 8.314. Use the gradient in D4 to calculate a value for activation energy. If you didn't find one, use minus 3100. Okay, let's do it. So log initial rate is equal to, I'm going to rearrange it a bit, minus activation energy divided by 2.303 R into 1 by T. Why did I separate it? Because 1 by T was drawn on the x-axis. So I tried to, rearrange it into this form, y is equal to mx plus c, where y is log initial rate and x is 1 by t. And that constant is basically your y-intercept. So minus activation energy divided by 2.303 R, that is your gradient. So I actually equated it with minus 2910. We got rid of the negative sign. By the way, I used my exact answer, the raw value. You could use 2910, it's fine. So activation energy is equal to 2.303 into the value of your gradient times 8.31. That value of 8.31 is given over here in the table. R is equal to 8.31, okay? So yeah, that's that. I'm getting a value of around, by the way, so this value that you're gonna get, it's around 55,749.5. It's actually in joules. Why? Because basically the gradient, what unit does it have? Log results in no unit on the y-axis, so it's basically no unit divided by 1 by t, which is Kelvin to the power minus 1. So that's basically Kelvin to the power 1, or Kelvin. That's the unit of the gradient. Okay, so the gradient has a unit of Kelvin. What about activation energy? It has a unit of, it's basically energy, so joules. But what about 2.303? It has no unit since it's a constant. What about R? Here I multiplied 2.303 into R into the gradient. So the gradient has a unit of Kelvin. R has this unit over here. R has a unit of joule per Kelvin per mole. Okay, so if you multiply joule per Kelvin per mole and Kelvin, you're going to get rid of the Kelvin and you're going to end up with joule per mole. But joule per mole is not the unit of enthalpy, it's kilojoule per mole. So to get the final answer, you need to divide your answer over here. Like I got this value for EA. I divided this by 1000 to get the value in kilojoules per mole because that's what they wanted, okay? So that's 55.7 kilojoule per mole according to my values. Understood? This is the working over here. Hopefully you understand. Please be sure to do this. At the end, let's talk about this party. It is not possible to repeat the investigation. The bold, focus on the bold word. It is not possible to repeat the investigation. In physics, you know that we repeat the experiment for each value of the independent variable to get an average value of dependent variable to increase the reliability, you know. But sadly here it was not, we were not able to repeat it. And as a result, reliability decreases. So no, this is because there is an anomalous point on the graph, and also because they didn't mention it over here, but we were not able to repeat it. But you will find two questions typically, like looking at the points on the graph, figure out whether it was reliable. Honestly, this data is more or less reliable because out of how many points here, 1 2 3 4 5 6 7 8, if your graph passes through 6 points, out of 8 perfectly, the data is usually reliable. That's one question that you're gonna face, okay, in previous question papers. You had to say that since it passes through most of the points, the data is reliable. You see these in 2016, 2017, 2018 variants like those. But this is a new form of question that has this is the first time I've seen this. They mention at first that it is not possible to repeat the investigation, and since we have an anomaly, this is greater proof that no, the data is not reliable. Okay, so this is the new pattern of questions that's it's coming. So if you do find this question on your exam on the 7th, please do answer it respectively, okay, according to the data on the question, given in the question, because this was not present before. If repetitions were present and if it passes through most of the points, it would have been reliable. However, here it's actually unreliable due to an anomaly being present as well as failure of repetitions. Okay, guys, that's it for today. If you like the content, remember to subscribe to the channel. I'm gonna link the paper for May June 2022 paper 5.1 or 5.3 up here after I solve that, and the paper for February March 2022 paper 5.2 down here, and the playlist for chemistry paper 5 up here. See you guys.